let's ramp up the difficulty. We first solved the heat equation on a stick, on a thin bar that was so thin we could approximate it by saying that it was one-dimensional. Here we're gonna look at the heat equation on a full disk. I use nabla squared and delta as interchangeable. They are the same thing. And now we introduce the domain omega, and we say it's a disk of radius c. So we change from Cartesian coordinate x, y to polar coordinate theta and r. Theta, if you have a point in your plane, r is the distance from that point to the origin, and theta is the angle that segment from the point to the origin makes with what we usually call the x-axis. So theta can take values between 0 and 2 pi, including 2 pi and including 0 and excluding 2 pi, and r takes only non-negative values. It can be 0, but it goes from 0 to infinity. In Cartesian coordinates, our nabla squared is delta squared divided x squared plus delta squared divided delta y squared. We want to make a change of variables. We want to go to r and theta. We can write it in two ways. Either we write r as square root of x squared plus y squared, and theta satisfying the tangent of theta being equal to y divided by x, or in the other direction we can write x as r cos theta and y equals r sin theta. If we want to change our nabla squared into the new change of variables, then we can take we need to transform delta over delta x into something that depends on delta over delta r and delta over delta theta. And we can do that with the chain rule. So we write delta over delta x being equal to delta r over delta x times delta over delta r plus delta theta over delta x times delta over delta theta. So now we're left with solving delta r over delta x and delta theta over delta x, but we have the formulas of both r and theta with respect to x and y, so we can solve that. I'm not going to spend a lot of time to show how this is done, but I will put a link to an explanation that goes more in depth about how to reconstruct the Laplacian in the new change of variables, in the new variables r and theta. Here, I'm just going to state that the full nabla squared in polar coordinate has this format: 1 over r delta over delta r multiplied applied to between parentheses r times delta over delta r plus 1 over r squared delta squared over delta theta squared. So if we are writing out all our heat equation in polar coordinates, so we have u being a function of r, theta, and time, then we retrieve this formulation: u t minus alpha squared multiplied 1 over r delta over delta r times r delta over delta r u plus 1 over r squared delta squared over delta theta squared u, close parenthesis, all equal to 0. I will put Dirichlet boundary conditions on the circle, homogeneous Dirichlet boundary conditions. So u for every theta, r equal to c, and for every time, so we're at the boundary of the circle, is equal to 0. And that t equal to 0, I'm going to give an initial condition that only depends on r. So u r theta for t equal to 0 is f of r. this is a graphical representation. We have the origin. Every point is defined by its distance from the origin and the theta angle to the horizontal axis. We have a distance c from the origin to the boundary of our region, and we imposed u at c for all time equal to 0. You might notice that our boundary condition, our initial condition, and in some senses our PDE itself don't depend on t. Don't depend on theta. The only place where theta appears is in the second derivative, but it's kind of self-contained. This gives an idea that what we're looking for is radially symmetric, which means that it doesn't depend on theta, it only depends on r. That means that whatever value you have, it's there around our circle. Now that we can get rid of one of the variables, in some senses we went from having a 2D problem to a 1D problem again. And we can apply separation of variables again. We say that u r t is a product between a function that only depends on r and a function that only depends on t. Theta disappeared because we are claiming that the solution should not depend on it. So our new problem is urt is equal to capital RR, capital TT, and we plug this into our heat equation in polar coordinates. The first thing we notice is that the second derivative with respect to theta of u is equal to 0 because there is no theta in there. So it simplifies to RT prime minus alpha squared divided by r all times r prime t plus r second t equal to 0. We can do some changes of things around, but with the idea of the separation of variables, what we want to write is an equality in which everything depending on t is on one side and everything depending on r is on the other, and we can do that. It works. And as before, we claimed that these two fractions, one part only depending on t and one part only depending on r, need to be constant, so we're going to set them equal to minus k squared, as we did before. We're now left with two different ODEs. We solved the one with respect to t quite easily, and then we're left with the one depending on r. We have minus 1 over r prime plus r second equal to k squared r. R prime plus r second is actually the first derivative of small r times r prime. And we have the boundary condition that r at value c, so at the boundary of our disk, is equal to 0. This is only one boundary condition for a Sturm-Liouville problem. That's not great, but the other boundary condition is going to be given by physicality. We want the temperature to be bounded everywhere. So we're requiring r at 0 being bounded. Makes sense because our Sturm-Liouville problem is between 0 and c, and at 0, our w is equal to 0. So we have to have r0 bounded there. We can write our Sturm-Liouville problem. We can write our differential operator h as minus 1 over r parenthesis ry prime close parenthesis prime, where we assume y is a function of r. Looking at this function, we recognize it as a Sturm-Liouville problem with p function of r equal to r, w function of r equal to r, and q constantly equal to 0. We can write it in standard form, hy equals minus 1 over w py prime in the standard form. We just, without solving it explicitly, we just know there are solutions. There is kn and phi-n eigenpairs with the Now here there is a mistake, there should be a W appearing in the inner product, but we know that the inner product between phi n and phi m is equal to 0 if n is different than m, and the inner product is defined as the integral between 0 and c of phi n times phi m times w equal to 0. I don't know why there is a c instead of a w. Then we know that our full solution can be written as an infinite sum of Cn times phi n times the exponential of minus alpha squared kn squared t. And if we normalize phi n in such a way that the inner product of phi n by itself is equal to n for all n, then we can write Cn as the inner product between f and phi n, that is the integral from 0 to c of r times fr times phi n r, where phi n plays the role of sine and cosine that we have seen before. So we're really using all the build-up of the Sturm-Liouville problem that we have seen up to now. And if we define the Cn's like that, then we're satisfying the initial conditions. If we want to solve for an inhomogeneous problem on the disk, so we're setting, we still want it to be radially symmetric, so we want u at the boundary of the disk, so for r equal to c and for every theta being equal to something, for example 100, then what we will do is find a steady state solution that solves the boundary condition, and then go back to the previous case in which we have changed the initial condition based on the steady state.